All right, ladies and gentlemen, this is our conservation of momentum lab. Today we're going to look at when two cars collide and stick together. So if you pull up your conservation of momentum lab sheet, you can find that on the Canvas page or in the packet for this week. I'm going to perform the trials here so you have the raw data to look at for conducting your lab calculations and analysis. So if we look at our lab description, trial 1 says that both carts should be empty. And as I've noted over here, each cart has a mass of 0.250 kilograms. So look at what we're doing here. One car is 0.250 kilograms. When they stick together, that's after the collision, then the total mass, MA plus MB, will be 0.5. Basically, we've doubled the mass after they collided, and now we have two carts moving instead of one. The goal of this lab is to see if momentum is conserved before and after the collision. So as we collect our data, and you look at the little box at the top of the screen, I'll hit collect using our Motion Detector and LoggerPro. I'll push the car, they run into each other, and then we conduct and stop our trial. Now there's this blue button up here, auto scale, and what we can see is our velocity and position graphs. And you see that our velocity graph here, we had a certain velocity there, and we also know that the slope of a position time graph gives us velocity. So on your data table, where it says before velocity, or VA initial, write that number down at the slope, 0.5526 meters per second. Now, why did the slope change? Oh, because the cars ran into each other, of course. And so over here, if I do another linear fit, keeping in mind that the slope of a position time graph gives me speed, this number would go right over here for V final. This is the velocity of the two combined cars after the collision. Write the number 0.2529. All right, so the rest of those calculations for P before, you're just going to do mass times velocity because that's how you calculate momentum. And you would do mass times velocity because that's how you calculate momentum. For percent change, you can see the directions and this little formula at the bottom for how you're going to calculate percent change for each one. And so our goal as we go through these trials is hopefully the percent change will be very small because momentum is supposed to be conserved. As we go on, trial 2 says to put 250 grams in cart A. So that's this one. So I want you to think before I shoot this here. All right, we have a heavy cart running into a light cart. Is the heavy cart going to change its velocity a lot, or maybe not quite as much? We'll see. All right, so there's our trial, and it looks like we didn't have too big of a change in velocity. Go ahead and write these numbers down. Trial 2 velocity before was 0.5218, and the velocity final over here for trial 2 was 0.3338 meters per second. If we read the directions, it says that trial 3 should have a added mass of 500 grams in it. So that brings our total up to 750. And let's run this trial and see what happens. Now we have a really heavy cart running into a really light cart. Let's see what happens to its change in velocity here. Okay, hardly any change at all there, because of course it's very heavy, it's got a lot of momentum, and running into something that's light, it's not going to affect it very much. So for your data table, we can go ahead and record our initial and final velocities. Our initial velocity for trial 3, according to our position time graph slope, is right here, 0.4079, and our final velocity is 0.2695. Now we're going to change things up a little bit, and if you look at trial 4, it says that cart A should be empty, so I'm going to take all these masses off of here, and that cart B should have 250 grams. So I'm going to put that right here on cart B. And now we have a light car running into a heavy car. Is that going to result in a big change in speed or a small change in speed? Let's go ahead and see what we observe. Okay, we saw a pretty drastic change in speed here, and that makes sense because something that's light and runs into something that's heavy, that light thing is going to be slowed down quite a lot as it imparts its momentum to the heavy thing. So again, we take the slope of the position time graph for before and after the collision, and we're going to record these values for trial 4. So trial 4 velocity initial there is 0.745, and trial 4 velocity for after is 0.2318. All right, I hope you're seeing the pattern here that we're just using the slope for before the collision from the position time graph because that gets us meters per second or velocity, and the slope from after the collision for our data. All right, one more trial here. This is trial 5. We're going to make this first cart empty, and the second cart is going to have 500 grams added to it. So this is a very, very heavy cart run into by a pretty light cart in comparison. So let's see what happens here. All right, again, we see an even more drastic change, but here's our initial velocity for our first cart, and here's our final velocity for the 2 cars moving together. So on your data table, the initial velocity was 0.7855. The final velocity was 0.1798. At this point, you have all of the velocity data that you need. You want to go ahead and calculate your P before and P after, and use this equation at the bottom to calculate the percent change in momentum. Then you're going to take the average of that, 5 numbers, add them up and divide by 5, and we hope to see a very, very low average percent change in momentum. On the back of the sheet, then, you're going to have some analysis questions to answer. So for the purpose, you can just see the front, talking about what type of collision. All right, you can think about, is this a bouncing collision, a sticking collision, or an exploding collision? And then for this one, is the percent change high or low for any trials? And what was the average? And explain why you think that average is good or bad in terms of the conservation of momentum. Finally, at the bottom, I just want to see that you know how to execute the problem-solving strategy. So you can flip back to your notes from yesterday, page 7, if you need a model for how to do that. But that's the final piece of this lab today. Happy physicsing.